All right. So we're done with the theory, and this will come up over a few more times, and so hopefully some of that got in, but do not hesitate to stop and say, okay, no wait, reflectance factor, why are we using that again? And I think it comes up maybe 9 or 10 other times in terms of what I'm going to do. Next is going to be the equipment discussion. And so based on the fact that we want reflectance, and we're going to use reflectance factor, that means that we'll probably use a reference standard in order to get to reflectance. And then we're going to need some sort of device to measure it. Those are the two key pieces, a radiometer and a reference. In terms of our reflectance references, one thing you could do is, so this is that chart that's repeated basically again. The ideal case would be to take this material, that PTFE, polytetrafluoroethylene, the halon, and it would be to take that powdered material, press it, and make it into a panel. Instead of using spectrum, we didn't want to use this powdered stuff that's pressed together. Anybody think of what might be a problem with trying to do that out in real life? Has anybody kind of walked along and then tripped or stumbled and then put your thumb in the middle of something you didn't want to put your thumb in the middle of? Okay, so fine. I'm the only one who does that. That's why we never use the press PTFE. But it just is not, it's not robust enough for field work. It works great in the laboratory, and so before I left the University of Arizona, we had a sample that had been pressed and had been in place for 3 years. And it had been just taken so well care of. It was in a tight case, it was airtight, it was put in a clean tent, and it was highly valued because it took a lot of effort to make that sample. We had to grind it up in a blender and measure it out carefully and press it with the right compression. And so it was a great day when somebody finally said, you know, we have to go ahead and make a new sample. And we all gathered around and basically put our fingers in the sample. You had to be so careful with it for so long that you wanted to destroy it. So when we did destroy it, we did. But that would be the perfect thing because now you know the reflectance factor. It's not like you have to measure the reference. You have the reference, and you can take it outside. What's nice is now the National Institute of Standards and Technology will measure spectrum the same way. So they will give you the reflectance factor of a sample of material. And a lot of the other metrologic institutes are doing the same thing. So the best thing you can do is take what we call a primary standard. We give a material to somebody who knows what they're doing, that is blessed by the governments, whether it's the Chinese, the Japanese, the Italian, the German, the English, the US government, and they say, this is the reflectance factor of that. You now have a primary standard. And there's no error in terms of you then using that for reflectance factor. So as I mentioned, it's not very robust. It's really hard to make it really big. The holder has to follow all kinds of specifications, and it has to be stainless steel, which is really heavy. And so we at one point, back in the 1980s, they pressed a piece of PTFE this size, and it weighed 25 kilos. I mean, it's heavy. What's really bad now is in the United States, nobody can get the standard any longer. So that makes it a little difficult to use this pressed concept anymore. Some groups have gone ahead and found replacements, and then they had the replacements evaluated by NIST, and so they have ways to still do a primary standard.
But I looked at the NIST report on that, and it only went to 800-900 nanometers originally.
They extended it, but it's not,
Okay.
Yeah.
I'm looking at an older report.
It's an old one, but the measurements out beyond 1 micrometer, 1,000 nanometers, are very limited because the absolute radiometers they use to measure the incident irradiance are not very well understood. The uncertainties are very large. Paints. So a pressed sample is pretty tough to work with. This is the other extreme. Paints are very simple. You can buy them in a can. You can go into and we even were using in some cases just spray paint that you would buy to paint your chairs or your wall, and you can put that onto a piece of metal or something. As long as you characterize it for bidirectional reflectance factor, it's fine. There's some barium sulfate, for instance, which They will not have spectral features, they'll be spectrally flat. And because they're bumpy, they also are very nearly Lambertian, so it makes the characterization of them much easier. But strictly speaking, if you're going to characterize for BRF, we could use this table as a reference. We would just have to make sure we characterize it and understand the uncertainties caused by using that sample and by characterizing it. Witness samples from space diffusers is one that was used in a couple of places. So when they launched the early Landsat systems, the early group at the University of Arizona had one of the witness samples that was used for the diffuser for Landsat. And one, it's kind of fun. This is something that's going to go to space. And two, is will allow you, if you took it outside, is you now have something that's direct traceability to whatever's in space. But it's costly and there's problems with how they degrade. But the expense is very low. So again, there's no perfect material. But even though there's no perfect material, periodically what happens is everybody gravitates towards that one thing. And Spectralon happens to be that one, that material. And there's other now companies that make it besides LabSphere, which is now Sphere Optics, which I forget what they're called. They keep getting bought by other people. But you take that fancy powder, you press it and you bake it. And there's a proprietary way they do it that gives you Spectralon. So it's more durable. You can machine it, you can carve it, you can carve out the inside and turn it into a sphere if you want. In this case, there's a gray panel over here on the left. There's a white panel. You can get it in sizes going down to very, very small little discs up to, I think, 18 inches is now the largest single piece they will make. Some of the problems is it has a large thermal expansion property, so if you keep it inside and it's cold and you take it outside, it can pop out of its container. In the old days, they would not make panels this large. They would make two pieces that were smaller. They would put them together like this because when it expanded, it would clamp onto it. But if it was cold, you now had a gap and a nice little shadow that you had to deal with. And so you had to orient it so that the sun would not create that shadow. It really has become the industry standard, I think, because of its portability. And there were 2 or 3 groups in the United States, Europe, and China that started using Spectralon and got excellent results. And so, of course, everybody believed that it was because of the Spectralon that we were getting excellent results. And in some cases, that's true, but in some cases, it's the fact that when you realize you need something like Spectralon, your techniques tend to be a little bit better, and there's other reasons that the results are so good. If you obtain this material from the manufacturer, and I still do not know of any manufacturer besides, I think there's a German company, I think there's a Chinese company that make a Spectralon-like material. Nobody provides the panel with bidirectional reflectance factor. They provide it with what is called an 8-degree hemispheric. And what that means is they will take your little sample and they will put it up against the spherical integrated source. So there's a sphere, and there's an opening. And they will bring light into that sphere at 8, or onto that material at 8 degrees. And then they measure all the energy coming off with the sphere. So that is not a bidirectional reflectance factor. And we'll see later on, that is important. This is, if you're doing reflectance space calibration, this is the biggest mistake that everyone makes, is they use the 8-degree hemispheric value instead of a bidirectional reflectance value. So we have different sizes. As I mentioned, we have a small version of a gray panel. We have a white panel. This one is an 8-inch panel. Here's a 6-inch panel. I apologize for the sizes. That's just the sizes we make in the United States, so 15 centimeters or so. When I was in Arizona, we developed our own stand, so this is what it looks like uncovered. There's a stainless steel cover that goes on top with Teflon that keeps it in place. And we had legs that allowed us to level it. So that allows us to pick it up, move it, set it down, orient it the way we want, and get it level so that we know the incident angle because we know the time of day. And by the time of day, you know where the sun is. And if your panel's level, then you know the angle onto the panel from the sun. And that was our dominant energy that we were concerned about. Panel requirements. So really all you have to have for a requirement for your panel is it has to be measurable. You have to have a way to characterize it for BRF. Once you have that, you could use tinfoil. aluminum foil, or aluminium foil for those of you from across the pond. The near Lambertian quality just reduces errors. It makes the characterization easier, but it's not a requirement. It is, I would much rather have a near Lambertian panel, but that's just, again, I like things to be easy. I like to concentrate my uncertainties. Spatial uniformity, though, is something that's really important because when you try to characterize bidirectional reflectance factor, BRF, your light source really should be a very narrow beam because the larger the beam, then you get angular effects that fall off. So the smaller we can make that beam, then the better off the measurement will be. But the smaller that beam, and you have non-uniformities, now instead of getting an angular change, you're getting a spatial change because the panel reflectance is changing with location as opposed to with angle. So if you were to ask me what's the most important thing on a panel is try and make sure you get something that's uniform. Lambertian's nice. Near Lambertian is okay, but uniformity is important. And for me, portability. And this can depend upon how strong you are, what you define as portable, but it should be something that's easy to use. And large size is much better than small size. Now, what's interesting here is you can really create two panels. You can get something that's a really good material, and then buy something that's a cheaper material, like even spray painted, and just surround it. And so that your one really important piece is what you're looking at, but you're just trying to control the amount of out-of-field light. And I'll have some charts and some pictures that show what I'm talking about there. So reference calibration, the difficulty, and I know Chris struggled with this as well, is everything we do, we try and reduce stray light in the laboratory, which means the walls are painted black, the holders are black, and everything is black except for a few things that are of interest. So it takes really bad photographs. The base of what you have here is a lamp, a radiometer, and a panel. And in this case, we're using it as a calibration where we're using a absolute understood source, incident on the panel at 50 centimeters and viewing at 45 degrees because we know the reflectance factor is unity at 45 degrees, which is another beautiful thing about spectrum. And that will come up again. The same setup is used in this another picture, but basically we're trying to get to this directional reflectance factor. So this is angle. In our case, it's the angle of incidence. So we have the panel, and we mount it onto a rotation stage. So if I'm the panel, I'm mounting it on a rotation stage, I can turn. And the radiometer is looking at me at what we call nadir. And then we rotate the panel relative to, I'll just do the light here is the light source. And we'll just rotate relative to the light source with the panel viewing normal, or the radiometer viewing normal to the panel. Because that's what we do outside. The panel goes horizontal, the radiometer goes vertical, and the sun is moving through the sky. So this gives us that directional reflectance. We do it as a function of wavelength. It's much better to do this in multispectral space because we want to make sure the radiometer is well controlled. So we have a really good radiometer, which means we stay away from, good Andreas is not here, we stay away from spectrometers because they have lots of features that you try to avoid when you're doing high quality measurements in the laboratory. And so then we have to do interpolations at other wavelengths, but what you notice is that there's a color to the panel. If there was no color, if it was white, then all of these would fall on top of each other. And then it falls off as you go to larger angles. If this were a Lambertian panel, what would this curve look like?
Cosine. Cosine.
If it was intensity, it would be cosine. But we're doing this is equivalent to radians. So it would be flat. So you're right in terms of if you're thinking energy, it'll fall off as a cosine factor. But if I convert it back to reflectance factor, because remember reflectance factor is ratioed to what a Lambertian system would give us, you would end up flat. The units here go from 0.7 to 1, basically 1.1 at the top. Is there anything in this graph that bothers anyone?
if it is a Langerhans panel, the different wavelengths is even though it is the flat, the line is still have different the different wavelengths you have there respective.
I could still have a what I would call, this is a yellow panel. I could still have a yellow panel, and they could all be flat, but they would still be separated. There's usually something though that when I show this graph that really bothers at least one person. And and if it doesn't bother anybody, then I've done a really excellent job. And either or I've done a really bad job. Either way, I make myself feel better.
Is it that the reflectance factor is over 1, but that's because it's compared to a sample, right?
Everyone goes, how can the reflectance be higher than 1? That's impossible. Reflectance can't be more than 1. All this says is that this particular material is brighter than a Lambertian material at that same angle. Now I cannot create a piece of material that would be above 1 at all angles. And so in this case, the total reflectance will be less than mu. It will be like about 0.99, 0.98, depending on wavelength. But it's because I have these things down here that are below 1. So reflectance factor can exceed unity. And that's the beauty of reflectance factor. So don't let that, and that's why I spent a bit of time, because there's going to be a lot of graphs. You're going to see this over. And it may not hit you now, but all of a sudden this afternoon you're going to be going, how do we get reflectance more than 1? And it's because we're not doing reflectance, we're doing reflectance factor. So I'm glad somebody brought it up, because that's exactly what I'm trying to do, is make sure if you do not see that as a problem, it means I'm probably not explaining it well enough. So that tells me at least somebody was understanding what I was saying by the fact that they asked the right question.
I've got 2 wee questions. If you normalize them all at 20 degrees, all lines up with each other, in other words, is there no spectral dependency on the question? But I've assumed that myself, that the reflectance factor, if they're all normalized, you follow the same curve.
We do see a slight dependency on wavelength with reflectance factor. Yes, it's not necessarily, and if you do the physics of it, basically what's odd is this material here is what I would call a surface scatterer. Spectralon is a bulk scatterer. Even though it seems solid, there's enough spacing between the particles that the photons penetrate, bounce around, and come out. And so the physics are that at short wavelengths you will get a slightly different scattering coefficient than you will at longer wavelengths, which gives you a slightly different BRDF. It's not a very strong term, because when you look at clouds, for instance, the atmosphere, it's the same concept that everything scatters about the same with wavelength and with angle because of the amount of scattering that's happening. But once you induce a wavelength dependency, even if you normalize that wavelength dependency, you have an absorption feature in there that is wavelength dependent.
You understand that?
And then that will lead to a change in the BRDF as a function of wavelength as well.
Can I ask another wee one?
Sure.
Please. If you said that if the panel was Lambertian, horizontal, you said that the total reflectance, I'm not using the wrong term, cannot exceed 1. If you integrated the area of that, would that match the hemispherical reflectance area? That's what I was trying to do a couple of days ago.
So the reflectance cannot exceed 1. And by that, it's albedo cannot exceed 1.
But the hemispherical, the large-scale hemispherical reflectance.
The 8-degree hemisphere. Yes.
And the area of that, over all angles.
I'm losing you on the area part.
Yeah. Okay, I'll try and draw it out.
We can check. So, in the facility that we had at Arizona, similar to other places, there's a lamp, and the person who designed this, Stuart Bigger, he is a true metrologist. I tell people is I'm a 5% kind of person. Stuart Bigger is a 0.005% kind of person. This lamp is at a distance such that the size of the lamp projects the same solid angle as the sun would onto our panels when we operate out in the field. So it's a geometry matching situation. Even though it's completely unnecessary to do that, we're after a biconical reflectance factor that matches sort of what you'd see outside. So that distance is such that it's there. There's a wall in between with an opening that reduces the stray light. And then the radiometer is mounted and pointed at the panel, and then that whole assembly is turned, and you make measurements, and that allows you then, if you put the PTFE sample up, do all those measurements, maintain the lamp at the same output, and that's driven by the power supply here, and then that's carefully monitored. And then you keep the same radiometer in place, you take the PTFE down, you put your spectron up, and you do the measurements again. Then everything gets normalized according to the way that NIST says you should do it. We've done this for barium sulfate, for Spectralon. What was unique about how Stuart designed it was, instead of making a system that makes measurements of samples about this size, he makes measurements of samples about that size, which is, again, better for us in the field. But it makes it more difficult to do round-robin comparisons with the national labs. This has been checked against those national labs.
Do you have any guidelines as to the distances on here? How far things should be from each other?
So this wall from that is basically the same as the ceiling to where it stands and the sidewalls. You know, you just don't gain anything but in terms of what size room you should have, bigger is always better, but do you take a room like this and turn it into a black lab, or do you use it for a conference room? And so there's always competition. If you basically get a perfectly absorbing material on the walls, then you can make it as small as you want, but that's the difficulty. It's hard to do that. It really is, it's one of those where you build it, you make a measurement, and then you make some additional measurements to see if you have impacts and effects because of walls, tiles, lamp location, and things like that.
So how about panel to radiometer?
You want to minimize basically the size of the spot as much as you can, but not obstruct or create a stray light of light bouncing from the optics back onto the panel and back onto the radiometer. And that was evaluated. And again, it depends on the radiometer that you're using, and so there's no true single answer. It's just, you know, if you have an ASD which has a small optic, you can get much closer. If you have a home-built radiometer we have, which is a larger optic, you have to go a little further away.
And just one last thing to follow up on that.
Yes.
The hole in the screen, I assume that's selected such that the diffusion effects are minimal there, or
Which effects?
the whole, like the whole size diffusion, you know, the light coming going through that. Are there
It's a
diffraction? Sorry.
Yeah, no, so it's big enough that the diffraction of the edges is not the dominant air source. It's a knife edge, so that cuts down the amount of forward scatter out of it. And he also has the advantage of it has a shutter in it. And
okay.
the shutter, even we can chop it if we want to. So to show you infrared, we have an instrument that needs to be chopped, and rather than chop it at the detector, we chop it at the source, which cuts down the stray light in there. If you ever want to see a machinist head get very large and eventually maybe just not work anymore, have them build a chopper that is 2 meters in size. So you basically have an object that's spinning, and you want it to be at 60 hertz in some cases. So you have a very fast spinning blade. We did not tell the people that we put it into the wall. So, of these two graphs, one of them is a white panel, and one of them is a not so white panel. And again, it's the same curves as before, where each of the colors is a different wavelength. So how many think that the not so white panel is over here? In these graphs, if the colors spread, that means you have not white. So this is a new panel, and this is a panel that's been outside. The It degrades with time. There's materials inside of the spectrum, contaminants, that as they photolicize, as they get exposed to sunlight, they change colors, they start to absorb. Is that a problem? Yeah, it would be nice if it never happened. But the fact that we know it is what's important. So that's corrected. So step one is characterize and correct, and step two is spend a lot of money and get perfect. And if you're in most laboratories, characterizing and correct is good enough. And you notice there is slight separation on these, and that's not, some of that's wavelength dependence, but it is BRF as a function of wavelength. So now, again, this is the same thing. It's basically a year apart. So calibrated day 1, calibrated day 365. You basically can see that things can change. You want to characterize that. But what you want to do is look at the fact that as the sun angle changes. So if I'm at a site where I can have a 10-degree sun angle, and I'm at a site where I can also have a 60-degree sun angle in the wintertime, that's not hard to do, I have at least a 10% difference in reflectance. So if I split the difference, I now have at minimum a plus or minus 5% systematic uncertainty that goes with season and goes with sun angle. And I've already exceeded all the error budget I hope to do in terms of reflectance-based calibration. And if I get larger incident angles, then it's even worse. And if I get some panels that are not in such good shape, then it gets worse there. So you really have to make sure that you're accounting for this. Now there are some things you can do, though, that are very, not sure what a good. I have a colleague at JPL, Rob Green, who does not want to do black lab measurements. Does not want to have a goniometer system. But he has an airborne system called Avros. So he can pick when this thing flies. So whenever he calibrates Avros, he always flies over his test sites when the sun angle is 45 degrees. Bidirectional reflectance factor is 1. It's just a quirk of spectrum. But they figured out where that quirk was, and they just make sure the geometry is always such that they're at 1. Now, one of the issues is they have to make sure they're making their measurements fairly quickly because the slope is pretty large in that range. So as you change sun angle, then you get larger changes in BRF, you get effects that happen as a function of time. Not as bad as at the other angles down here, but if you were going at 20 degrees, then you would have a smaller change with time, but you just need a correction factor. So there are ways to get around the fact that you may not have a device to help you get the bidirectional reflectance factor. But step 1 is use bidirectional reflectance factor, not bihemispherical or hemispheric conical. And if you can do it, make sure that you can either measure it or that you're picking a time for which you know what the values are. And you have to deal with the fact that if you play that game, you want to make sure you're cleaning your panel. So they figured out how to sand the panel and refresh the whiteness of it. That worked out very well for them. So step 1 is make sure you don't hurt your panel. So we cover it when we carry it, we cover it when we ship it. We used to basically make measurements of them after every trip and realized that they weren't degrading that fast. And there's a higher risk that you take them out of their case and put them up on something vertical. And you have all sorts of things moving automatically. We had early on in testing, we drove a piece of radiometer into a panel that was a painted panel, so you learn that sometimes you just go ahead and you don't want to ruin your press PTFE or you don't want to ruin the field reference, so you just assume that it's okay over a 6-month time period.
For the charts you showed maybe 2 or 3 slides ago where it was a full year of use and then kind of you saw the spread, in that year, how often was the sample used? Was it every day, every other day? So like, basically, what is the rate of decay there?
That was what we call our constant panel setup. So we would operate panels that we would use for reflectance, but we also had one that we had sitting out all the time. That in the morning you would set it up and you'd have a radiometer staring at it just to keep track of cloud conditions and sky conditions and help us correct for the measurements if we wanted to as a function of time. That thing was exposed for more than 30 days, for more than 6 hours on those 30 days. So about 180 hours of exposure, which is a lot for these things. Yeah, good question. So that's the reference. So I'm halfway through. This is taking a little bit of time, but I think it's still, everybody seems engaged, so I think we're not too bad off. I can go through the results a little quicker because I think it's the background that's really important here. So the next thing we need is something to actually make the measurements. We need a radiometer of some kind. And most groups right now are using analytic spectral devices, ASD, field spectrum, FR, I forget what the R is. Field spec, full range, the full range. And the reason that a lot of groups ended up this, and they've been now, it's about 20 years that they've been available, a little more than 20 years. When they first came out, the group I was with was basically trying to build our own. And it ended up being liquid nitrogen cooled. It was this big and was portable, but it weighed 35 kilos. So not quite as heavy as the PTFE big sample, but nobody wanted to carry that around. Once we knew that we could get this ASD, and we knew the developer, the name Alex Getz is fairly famous in imaging spectroscopy. He's the person who started ASD. They had a BNIR version that had been around for many years. And what was nice was we talked to a lot of other companies and really got no help. And ASD was the only one that was helping in the mid-1990s, so we ended up using the ASD. And then what the philosophy is buy it, characterize it, understand it, and then use it as much as you can. And then people just said, well, what is, when you using this ASD? And they started buying ASDs, and now everybody, we did a field campaign out in Turkey, and every group except one had a field spec with them in that farm. So we could all be biased now because of this one instrument. So it's nice that we're starting to see some new instrumentation come into play. Air fiber, 34-degree field of view. The Arizona group typically uses an 8-degree field of view. You can also get a 1-degree for it. The problem with the 34-degree is if we're after bidirectional reflectance, and we're really measuring conicals, so we're getting a biconical, and we can control at least half of that. I'll talk about the other part, because bidirectional means that we're directional coming in and we're directional coming out. Let's talk about coming out right now. Which of these two, the 34-degree or the 8-degree, is closer to directional? The 8-degree. So you're better off using an 8-degree field of view for directionality. There's a problem, though, with using an 8-degree field of view instead of a 34-degree field of view. I'm standing here and I'm holding up a radiometer and I'm looking at 8 degrees. I see a spot size about that big on the ground, between 5 and 10 centimeters. 34 degrees from that same height would give me a much larger spot. So I get angular effects, but I get a larger sample. Now, it turns out in this particular situation, though, with the way the optics are set up, you don't really change the amount of energy going into the system in either case. You lose a little bit with the 8-degree than you do over the 34, but it's not a factor of 5 or 6 like the field of view would indicate. Okay, so the fiber itself determines what the signal to noise of the system will be. This is really conditioning the angle of the light coming in. And we would attach it to a boom arm of some kind to get it away from your body so that you're limiting the amount of impact you have on it. We did not worry about clothing. I'll talk some more about that as we go on because that seems to get a lot of people worried. What you do with the fiber can play a role because the fibers themselves are somewhat fragile and you have to take care of them. So there are effects with the fibers wiggling and moving that you can tell. But this is a kind of a basic setup. There are multiple models of the ASD that are out there. So there's the backpack form. Yes?
What about shadows? I mean, I'd imagine even at a small size, they are casting shadows in front of the person is. So aside from being careful of it, are you tracking kind of orientation and some angles that you can deal with that?
So, yes.
Yeah.
So right here, you can just see just a little bit of a shadow right there. And that's, I knew where to look for the shadow because of how it's oriented and how we're measuring. You can see the shadow down here on the ground. So if you have an 8-degree field of view and you're looking straight down, then as long as the sun angle is larger than about 10 or 11 degrees, then it's technically not a problem, but then you're wiggling and moving. The real issue is that, you'll see this as we sample, you're walking. So I'm going to try and walk so that my shadow is somewhere over here. The instrument's going to be shadowed somewhere over there. And then we would stop and we'd turn around. Hopefully the person is smart enough to remember to flip to the other arm and walk back this way. That's this person's job. This is the most important person we have in every field campaign. Not the person carrying the ASD, the person watching the person carrying the ASD. You look a little tired, you look a little hot, you're not optimizing your system, you're not standing over the panel, you're kind of drifting away. You have a shadow, you might want to consider flipping around. And a lot of times it's just, okay, let's take a note, and you realize that that whole collection needs to be deleted because it's no good. So it's, again, all these things that they're going through, these are things that you see them and you just go on, okay, is there a way I can minimize the problem?
Does the instrument have some sort of an anemometer though, so you can see the orientation of the aperture?
No, on one of the devices we put on a clinometer, an electronic clinometer, and we logged that. But that was one because we were doing a system that was looking at 60 degrees. And so we tried to mimic that 60 degrees. And what it was then when you flip around, you either have to walk like this, move over and walk backwards, or you have to then flip. And so that was really the reason we were monitoring, was to make sure we had flipped it properly. It really is just trying, the 8 degree allows you to have a little bit of wiggle and bounce that, but some of the scatter we have in our results is because of that.
We comment also on the shading issue. What we always tell our students is directly facing the sun or directly having the sun in your back, of course, therefore also producing a bit of scattering. But this way you ensure them not to cast any shadows. You set up a,
And so the panel here is aligned for that particular reason. Well, to make sure the panel is being used the way it was calibrated in the lab, and it reduces the profile of the person, because the dominant scatter, the sunlight's going to be off of your main body, but it's going to go forward. It won't go, your solid angle that you project onto the panel is much smaller, which is why we did not worry about our colors and the fabric and things. Mostly because also this white material out in the near infrared is bright. So this shirt here is basically bright throughout the entire spectrum. That shirt is bright basically beyond about 600 nanometers, and it's as bright white as this material is. If you ever get a hold of a field spectrometer, any kind of spectrometer, look at fabrics. I mean, it really takes advantage of the fact that our eyes are really bad spectrally, and they make no effort to make the dyes absorbing out at long wavelengths. They reflect like everything else, and it's basically having a white fabric.
I've got to stop here.
Yeah.
You said something I've not heard before. You oriented the panel the way you calibrate from the bottom. Are you aware of a orientation error? Okay. Orientation
There are subtle effects in the out of plane of the spectrum. So when you start getting into the sub 0.5% kind of goals, and the reason we knew about it was we had characterized some flight units. And on flight units, they're trying to get to there was something going to Mars that was being characterized in our lab. And they wanted to make sure they were getting the exact geometry, and there it wasn't a nice uniform, it was kind of an odd geometry that they were doing. When we started to make sure we did that, so this was brought up, we had NIST come out and watch us on a field campaign. They said, well, you don't seem to worry about how you orient the panel. And we went, well, it's a really small effect. And so in terms of what we would see, it should be a small effect. But the minute we instituted that procedure of make sure that this front light here is aligned with the shadow of the sun, and then we would make sure that when we calibrated in the laboratory, we maintained that same geometry, all of a sudden our repeatability got much better, significantly better. But it had nothing to do with the out-of-plane issue. It had nothing to do with that, because that effect should not have caused a significant change. It was that everybody got better at leveling, because they now were careful about how they were setting up the panel. And it was just the overall of making somebody stop and think before they just kind of set it down and just take it and walk away. And now it had to be, they set it down, and then they would rotate it, and then they would, oh, and now I have to level it. It's just, it was an odd secondary effect that happened.
That one, sorry.
Usually, different people have different measurements. So the downward method, the stability of the height from the sensor to the panel.
So this person here is much taller than I am, and then we basically have this distance here, the distance to the ground, so tall people are a little bit higher than others. We always would maintain, in terms of the height here, is you want to make sure that the height is small enough that you have a view that's completely on the panel, so that all you see is the panel, but it's far enough away that light coming off of the panel onto the optic, back onto the panel, and back into the optic goes away.
So the pattern is to be controlled.
So in this case, for me, it was, I had a spot on my hip, and then I had this person here would tell me whether this was level. Or we also started putting levels onto the blue mark, so I could get there, and I would just look like this, I could see the level, and make sure that I had something that was appropriate, or at least it was the same height. So once I figured out what the height was that was appropriate, I just always did it that way. And the students that we had, they were either a little bit taller or the same height, and they essentially they copied, and that helped. But when you're walking, this starts to happen, this happens. You just try to be careful as you make the collections.
It seems like there's a number of ways for error to be introduced in this. Have you or anyone else just used like a robot of some sort to fixed arm and that thing?
We tried what we call the reflectable deal, where they, at White Sands, they were driving a vehicle and carrying a trailer behind it, and that was one thing. Some folks have tried bicycles, others have used all-terrain vehicles, the buggies. We tried backpack frames, we came back, so basically we always came back to this. This was the human is just so much better at controlling the surface and the movement. And what you'll see at the very end is this is still, we now realize is not the best way to do it. And there's a better way to do it that I'm hoping that if I can get it out there, people will realize it. Get a tripod, put it on a tripod, and set, stand back, collect. And it's just a matter of changing the way we do collections now. This method was one that worked very well at the 3 to 5% level. If we want to go that next step, the question that was raised by this gentleman, what about the height? How do you know you're in the same place in the panel? Now, those things have to be taken care of if you want to break that 2% kind of number. UAV, I always had what I wanted was, I called it a reflective balloon. I thought what I could do is put a stake in the ground on one side of my test site, a stake in the other, have a cable, and have a balloon DSD across the site like that. So UAVs would be really great, as long as, again, you can keep them stabilized, which are getting much better. The problem with them are, most groups are spending nearly $100,000 US for these type of instruments. They're getting better at being automated, so you can use them on something like a UAV. But I'm not sure I would trust my $100,000 investment for my most important measurement to then put it on something that could crash. And that was why we never went to that approach. I've known folks, there was a Japanese Honda back in, not the company, but the professor, back in the late 1990s, early 2000 time frame. He put an ASD onto a remote controlled helicopter and obtained some very nice results over vegetation sites.
For the Morris calibration or something like that?
Say again?
Morris calibration or something like that?
Yeah.
So he is Dr. Honda is my my former boss in
He was very well, because he brought his helicopter to Arizona. And
very powerful, but the UAV is a little bit not so powerful for, because the field spec is a little bit heavy. So the maybe a remote control helicopter is better for the field spec meter.
If we were to move towards something, instead of if we were doing reflectance-based calibration from a higher altitude, UAV. And you could get a good imaging spectrometer that was low stray light, that you could trust its calibration, then I think you have something that's a great idea. Carrying a field spectrometer in a UAV, I think, is really it's a waste of effort to get them on. There's not going to be a strong positive payoff of doing that with the non-imaging spectrometer that's a field system. I think if you could build your own high-quality radiometer and put it onto a flight platform, that's a better idea. I would not use a commercial off-the-shelf system. Other instruments, I just list them here. There are some other ones. In some of these charts, I'll go just kind of show them, make sure that you know the material is there, that you can find it. This is Kohei Arai from Japan Saki University. He has his own radiometer, or his own spectrometer that he built himself that I had never figured out exactly what it looked like, but he would just open up the case and start collecting data. One thing to keep in mind is almost all of the systems that you will see now are single-pass monochrometers with a grating, which is really disappointing. In the late 1980s, GER had double-pass systems. Fantastic instruments, very heavy, very bulky. Unfortunately, what's odd is if they had never tried to change the design, we would not be collecting the way we are today, and we'd probably be getting much better data right now, because we would have ended up collecting back then the way we've now realized we should be collecting now. Because the weight would have stopped us from trying to carry it across the site all over the place. We would pick it up and move it and stop. But these grading systems have a lot of stray light to them that needs to be characterized. You have to understand that it's in there. We would, strictly speaking, you should correct for that stray light. We're not to a state where we can do that easily. The characterization of that stray light is the problem. But again, I was talking yesterday is trying to break that 2.5%. There's all these little scattered things. And stray light within the gratings of these systems is one of those things that cause part of that problem. The spectral calibration, what's nice is, at least on all of the grading systems I've dealt with, I have not seen drift spectra in these systems. They are just wonderful in that regard. The airborne systems tend to drift more than I've seen in terms of these ground-based field spectrometers. Using the ASD, there are some wonderful little features to the ASD that you learn over time. They have gotten better. The early system like this one, they have a cooler for the slur detectors, and that heat from that cooler is dumped onto the silicon detector. The silicon detector is thermally stabilized, but when the outside temperature is around 40 Celsius, things start to basically fail. And so what you're supposed to do is warm up the ASD so that it reaches a stable temperature so that you can correct for all the features that happen spectrally in the detector package. But when it's hot outside, if you heat it up too long, you cannot collect the test site before it fails because it overheats. And I cannot yell at ASD, this is not their fault. You know, you just cannot conceive of these things. But I can yell at them for having a plastic case with no ventilation. The ventilation then became a fan underneath the computer, so it really wasn't true ventilation. It just, when you are doing things one way and you design it that way and other people are using it in a different way, you have to understand your instruments very, very well. And the features that they have, you have to figure them out either through time and effort or through lots of measurements. Battery failure, fiber optics fail. We got very good at understanding how long we could go before the batteries would die in certain field campaigns. A lot of times it was the computer batteries, not the spectrometer batteries. We would take multiple instruments with us in case we had failure, because this is the most important measurement you are making. And we were driving 15 hours to get to our test site. So you did not want to drive 15 hours and find out that your spectrometer was not working. But they are expensive, so having 2 or 3 of them is not a trivial thing either. The gray standard was something we implemented as a means to improve the statistics of understanding the instruments and to get what we call the type B uncertainties. And then maintenance was something where we did not want to get to this field site and find the problem. We wanted to be able to see it before we got there, so we tried very much to maintain as opposed to try and find out what the problem is. too late. I put this in here because we're talking equipment, and most of you don't think of the test site as the equipment, but how you actually set up your test site and where it might be located and things, you can think of it as a piece of equipment. And this will come up in our survey discussion, but the methodology we use is we would go out and we would lay survey flags to mark out lines that students would walk, and it just would make it easier because I could develop a technique and tell people, okay, here when you get to the site, here's how you lay out your flags. And then here's how you walk those flags. And the odds of at least one person on the trip knowing both processes was very good. And whether it was the person with the ASD or the person with the notes, somebody was helping to make sure that we were collecting in a repeatable fashion. And it wasn't so much that we wanted to make sure we were repeatable, but that our protocols were being followed. And of course, we weren't ISO standards, so we didn't have good manuals. We didn't have any manuals. Everything was just word of mouth. And so you would just go to the site and somebody would say, well, here's what you do today. And it's not really great practice, but what we did was instead of writing manuals, we developed methodologies that were more immune to people not following direction. Other instrumentation, this is for BRDF. So now we want to, if we have an ASD, we're typically only measuring the reflectance factor, looking straight down. This system here, there's basically a spectrometer here that goes up and down on a rail, and then this spins around this way, so you get all the azimuths and all the view angles. This is what they call PIGOS. There's also EGOS, which is in the laboratory. This is a European system. I'll steal, like Chris did, at some point I'll steal the system that they have at NPL, so I have another version of it. In the late 1980s, 1990s, there's a system called Parabola. Each of the little telescopes is a different radiometer with a different spectral band. The one on the left is the same as the one on the right. So you basically have two identical sets of 4 bands. And this thing spins and turns in zenith. And so it gets all the sky incident energy and it gets all the reflected energy of the ground. It does BRDF, but instead of it doing BRDF by looking at the same piece of ground, by rotating this way, it basically looks all over. So you have a homogeneity issue to work with, but you're sampling a little bit larger area, which is kind of nice. The Semel sun photometer can be outfitted to do this as well. So if you have a sun photometer from the Semel company, you can ask them to basically give you one that will do BRF measurements as well as do sky radiance. We developed a system that was a CCD camera. This was back when, in the late 1990s, when digital cameras were becoming easier to get a hold of. Not quite as simple as it is now, but it was still something that we put in a filtered system with a fisheye lens. The idea was that you then look down, so this is like a parabola system, but it doesn't have moving parts. It failed eventually, and it just wasn't worth fixing because cameras were getting so much cheaper. And by doing the processing over Ivanpah and Railroad Valley, we also determined that it just wasn't worth the effort because the systems that we were calibrating, the radiances that we were getting at the top of the atmosphere based on the atmospheres that we had, the impact from a VRF was not important. We found that we were having to make sure that we simulated the view of the sensor, but the diffuse light caused by the true bidirectional reflectance of the surface was not a large impact. I'll talk some about that later on this morning.